Now, you've probably all heard, or I hope you've all heard of the periodic table. And it lists all of the elements, both natural and also man-made, in increasing order of atomic number, Z, moving from left to right. Here we have the first two groups in the periodic table. I'm showing you here an extract from the first two groups, where we have hydrogen, H, lithium, Li, sodium, Na. Remember what I said, sodium actually relates to the Latin natrium, okay? Hence the reason why it should be potentially SO in English, but the reality is it comes back to its Latin roots. Beryllium, which is the fourth, and magnesium, which is in the third period. Now, as you can see in the periodic table, you can observe we've got a number of different numbers above and beneath the chemical symbols. If we look at the number above, it is the smallest number, and therefore it is the Z number, or atomic number. This correlates to the number of protons and the number of electrons that that element possesses in its atomic form. And as you'll see, you'll understand why I say atomic form, because a lot of elements in nature don't exist as atoms. They actually exist either as ions or they exist as molecules. But for the purposes of explaining basic atomic structure, we consider them in isolation, whether they exist like this in nature or not. As you can see on the board, I've introduced another letter there, A, which correlates to the atomic mass. Okay? Now, notice the atomic mass here is larger than the atomic number, and it correlates to the number of protons and the number of neutrons, as I've said earlier. Also, take note of the fact that the numbers are not whole. And this is because in the periodic table, you have to take into consideration the different types of isotopes, which have different masses overall, when calculating the relative atomic mass. And I'll show you how to do that in a second. Right, so here we have an example of how you would calculate the relative atomic mass of chlorine. And here, as you can see, they are proportional to their abundance. Now, recall what I said. 75% of all chlorine atoms exist in their 35 atomic mass form, whereas approximately 25% exist as the 37 atomic mass form of chlorine. So what we need to do is we need to find a weighted average of those two isotopes to give us the relative atomic mass that you would see in the periodic table. Now, I'm not going to go through this entire equation with you. Suffice to say, conceptually, it's relatively easy to do. Let's say, for the sake of argument, you had 75 atoms in one hand, each weighing 35 grams, and you had 25 in the other hand, each weighing 37. All you would have to do is multiply the mass by each percentage and then average the two. That's effectively what we've done here. This gives us an average atomic mass unit for chlorine of 35.5. Shown here is 35.45, but on most periodic tables you will see it's rounded up. And whilst the structure of the nucleus is important in radiochemistry and physics, in terms of the chemical characteristics, an atom of chlorine 35 will behave the same chemically as an atom of chlorine 37. It makes no difference to their reactivity. The only way you can even detect this sometimes is via certain analytical chemistry techniques, which are beyond the scope of this course.